Hello and welcome to Unit 12. This is going to be air-sea interaction, and we're going to talk about how the water gets from the ocean to the land and from the land back to the ocean, sort of like the water cycle, which we talked about in Unit 11. But we're going to talk a little bit more about the wind patterns that are driven by land and water temperature differences, and as well as local winds, global winds. We'll talk about ice, and we'll talk about sea level changes between land ice, like on Greenland, and water ice, actually up here in the Arctic Ocean. And one of those will be changing sea level, the other one may not be. Okay, so let's get to page 1. Oh, while we're here, I've got a new draw color icon that you can take a look at. When you see these, I would like you to draw the diagram that's there, and I'll point to the diagram, I hope. So 12A, and this is going to be the last unit we're going to do, so I think we have 3 more videos, including this one, so not much more, and then we get rid of that whole obnoxious class of 2016, or if you were watching this next year, the class of seniors. Okay, so oceans of air and water. Atmosphere and ocean is one interconnected system. Water goes from the ocean into the air, and it gets back into the ocean. So it's interconnected. It's the change, if you change the atmosphere, it affects the ocean. More rain, more water into the ocean, more fresh water into the ocean. And if you change the ocean, heat it up, then we're going to get more atmospheric water. So they are interconnected. And both have waves and act like a fluid. Wind moves, runs into things, goes up and down. An example of that would be like mountains. If you take a look at this, this is a picture of the Earth with cloud cover, and these are mountain peaks. And what you get is you get wind moving over the ground, and when it hits a hill or a mountain, in this case, these peaked mountains, the wind goes up, and then it goes down, and then it comes back up, and it actually makes these waves. And we'll learn later on, as the air moves up, it cools, and if it reaches the point where we get dew point, we may even talk about a skewed T model. I'm not sure whether we're going to talk about that because that's pretty heavy meteorologically speaking. But when it actually goes up and reaches dew point, the lift and condensation level, what happens is the air condenses. The water condenses in the air, makes clouds, and then as it comes back down, it heats. Goes back up, it cools, comes back down, it heats, and you actually get these waves inside the clouds where you get blue sky sort of in the trough, and you get clouds on the crest. This is all driven by unequal heating. I had you draw this back in Unit 11, I'm pretty sure, and you talked about the sun's rays being more concentrated. Sun's rays hitting the equatorial region more often than it does the polar region because of the tilt of the Earth. So you can see that this northern section is not getting any sunlight whatsoever. The southern section is getting as much as it can, and the equator getting bathed by sunlight 12 hours a day. So that actually has an effect. So low latitudes receive more direct sunlight, smaller path of direction, and because of that and more hours, it is a much hotter area. And the upper part gets more or less direct, more spread out light, and actually gets fewer hours of the sunlight, so it actually is going to be cooler. Equatorial regions receive excess heat. Polar regions have a heat deficit. If you take a look at how much heat hits the equator, they actually get more than leaves. So the outgoing heat is here, and the heat gained is picking up this. But then that, of course, moves into the poles, which actually loses more heat than it gets. So the poles actually are heated by this hot air, and then the cool air comes down and cools off the equatorial regions. Calories per centimeter per minute, and the equatorial region gets quite a bit. Isolation factors, latitude. If you have low latitude, you get lots of insolation. Insolation is sunlight. Thickness of the atmosphere. Thicker the atmosphere, it can actually have more clouds. And it's thicker at the atmosphere because it's warmer. Warmer air expands, and we have a thicker atmosphere at the equator than we do at the poles. These are the locations of the jets. We have a polar jet, which affects us in the wintertime because it actually moves down into southern United States, and we get this nice cold air coming from Canada. And the subtropical jet actually affects us in the summer when it moves north of us, and we get this nice humid air coming out of the Gulf of Mexico. So we get these convective cells. This is called the Hadley cell, the Ferrel cell, and the polar cell. And then we actually have high pressure areas, low pressure areas, and high pressure areas by the pole. And we'll talk more about those. We have the trade winds that are located right here that you used to go from Africa to North America back in the day. And then you have the southwesterlies where you actually moved from the United States back to Europe. And then they went along the coast back to Africa, and then they came back to North America, and they just kept doing that over and over and over. This is called the ICZ. The ITCZ, Intertropical Convergence Zone. This is where air from the southern hemisphere collides with air from the northern hemisphere and actually goes up and makes the tropical rainforest. As that air goes up, it condenses, lifting condensation level, condenses water, and if the clouds get big enough, it rains back down. We get another nice rain up here around 60 north, where we have what are called the horse latitudes here, 30 degrees north, and we have the polar desert area up here at 90, and also southern. We get those same things. Albedo, this is the amount of light that actually hits the earth and bounces back. Snow bounces back 80 to 95%. That's why on a sunny day you do need sunglasses, because you get the sun coming through the sky and you also get the sun bouncing off the snow. Forest, not as much. They actually do absorb some of that sunlight. That's what the green stuff is. Cropland, about the same. Grass, about the same, maybe a little bit more because it's kind of shiny. Asphalt has very little albedo. Most of it is absorbed. It only bounces back 5 to 10%. Concrete, a little bit more. And then the Earth's albedo is what's called 31%. We bounce back 31% of the sunlight. The moon actually has an albedo of 6 to 8%, or actually it absorbs 6 or 8%. So it actually bounces back quite a bit. So water bodies actually bounce back 10 to 60%, depending on the angle of the sun. If it's very low, it bounces back a lot. And if it's a very a very high angle, it actually goes into the water. But remember, it only goes down to about 300 feet, 100 meters, and then it's pretty much all gone. And then the seasons, when we actually tilt toward the sun, we receive more sunlight. Of course, we bounce back more. We still have a 31% albedo. If you're covered by snow, you're bouncing back more than if you're actually got dry dirt or dark soil. But all that stuff is there. And then the time of day, daytime, much warmer than it is nighttime, usually. And vegetation, bare rock. Vegetation actually allows more of the light to be collected, where bare rock may actually send up more. Okay, this is an interactive, and I have it stopped here at September. This was the fall equinox, where the sun's rays are actually hitting the earth, one hemisphere the same as the other hemisphere. I put us up here at about 37.9. We're actually at 38.6, so let me drop us down a little bit. I'm sorry, put us up a little bit. 38.5. That may be about as close as I can get us. 38.5. So this is the us in Dumfries, Virginia. This is actually the latitude of our classroom. And that is 38.6 degrees north latitude and 77.4 degrees west longitude. Remember, southern hemisphere negative numbers, and the western hemisphere negative numbers, because Europe came up with these numbers. So what we're going to do is we're going to imagine us here, and I'm just going to take this and move it, and you'll see two things. If you watch this one first, you'll actually see how the earth moves around us in a counterclockwise direction, and as it moves around us, that tilt of the earth, this 23.5 degree tilt, is always towards Polaris. It is always pointing in that direction. And because of that, at this point right here, which I hope is around December, I need to see, yeah, right about there, around December 21st, 23rd, that is the winter solstice, when the Antarctic Circle is completely lit up, the Arctic Circle is completely dark. Light's hitting the Tropic of Capricorn and goes all the way up to the Arctic Circle, and the Earth just rotates here, and you can see the northern hemisphere is in more, like we're located right here. And if you actually watch that rotation, if we rotate it all the way around, we would actually notice we would get more darkness on this side than we would sunlight on this side. Also, the angle is actually pretty low, as you can see with this picture. So our winters, not as much direct sunlight and not as many hours of sun, so we are cooler. If you look at the spread, you can actually see that the light is spread out. If I move toward the poles, you can see it spreads out even more. And then when I get to this Arctic Circle up here, you notice the sun disappears and I'm in darkness. And then if you go down here to the Tropic of Capricorn, you notice the sun is most direct. So most of the direct sunlight is located directly opposite this limb or this dark line, and that's where the sun's rays are hitting. So if I move us back up to about where we are, and if I move the Earth over to this location, now the Earth is striking the equator, and we're getting a smaller angle of spread. We're getting more direct sunlight, and actually, if you watch that direct sunlight, we get most of it right around here. And you see it's not direct because the sun's hitting here at the Tropic of Cancer, and we're really close to it. If we were located right here, the sun would be coming straight down, the most direct sunlight, and if you look at the spread, it's the smallest spread. So as we go toward this limb, either direction, the light spreads out. So if I just go through, there's the September, the fall equinox, winter, solstice, and then we move to the spring equinox, and we're moving toward this date, which we're out of school. This is the longest day, actually my wedding anniversary also. But if you actually look at the seasons and eclipse simulator, SWF, you can see this, but again, it's not in an Apple program. Okay, in the last slide, we're going to talk about the layers of the atmosphere, because this is going to be an activity we're going to do tomorrow. And you start with the troposphere. This is called the weather sphere. And you notice Mount Everest, the tallest point on the planet, 29,028 feet. It should be, I think, not 29. But anyway, if you take a look at that, all the Earth's surface is in the troposphere. Stratosphere is called the layered sphere. This is where air is moving. At troposphere, the air is moving up and down. Stratosphere, it's moving pretty much side to side. It's a good place for jets to go. If you take a look at the troposphere to the stratosphere, the temperature decreases, and when it actually gets to the point where it is the coolest, we call that the tropopause. It's the stop area of or the pause area of the troposphere. Then it moves into the stratosphere for the stratopause. Temperature decreases again for the mesosphere up to the mesopause, and then we go to the thermosphere, and that goes out, and it's called the thermosphere because it actually gets warmer up here. Very few molecules, so you'd still freeze, but the molecules that are up there are moving much faster than they are even down here. But this is where we actually call the 1, 2, 3, 4 layers. Some people actually say exosphere, but these are the 4 main layers and the 3 pauses that actually separate them. Tropopause, area closest to the Earth. It's the most dense air. It's the one that has the weather. Airplanes fly at the top of it into the stratosphere, 10 miles up, and most of the atmosphere, and we're going to find 80 to 90% of the atmosphere is in this first 10 kilometers, or first almost like 8 miles tall. Stratosphere, ozone layer is located up here. This actually protects us from gamma rays. It also helps shield the Earth from, okay, I said that. It goes up to about 30 miles. Ozone layer is there. This goes up to about 50 miles, or excuse me, about 50 kilometers or 30 miles up. And you can notice that we start at 1,000 millibars. 1,013 is what sea level is. It goes up to 100. This is the logarithmic scale. It goes to 1, 1/10, 100th, 1,000th, and it gets almost no air up here. You have a really tough time above 10,000 feet to actually, if you go up about 10,000 feet, you have a tough time breathing because the air gets so thin. Then we go to the mesosphere, the coldest layer of the atmosphere. And it's actually where the last point that the asteroids or the meteors actually go. The air gets too thick and they usually get vaporized at this point. Thermosphere, the area actually where we increase. We also have the auroras up here. It actually protects us from high energy alpha waves coming from the sun. And then we have the exosphere. This is where the satellites are, and they're actually going around the Earth. And I'm sorry, we have one more. Atmosphere, troposphere. Atmosphere is made of 79% nitrogen, And remember, nitrogen fixing bacteria pull it out of the atmosphere, so it's utilized by life. Atmosphere is 21% oxygen. This is the molecular oxygen you need to survive. It's also made of almost 1% argon and somewhere between 0 and 4% water. Carbon dioxide, very little carbon dioxide, but it has a much, actually water vapor is a much better greenhouse gas, but carbon dioxide has a very big effect on the greenhouse effect. Temperature decreases with increased altitude. As you can see, the temperature goes down as we go up. And there's where we actually get to that 10 kilometers. And this is going to be the tropopause, where we actually stop cooling off and start heating up. It's warm, less dense air actually goes up and cools and makes clouds. And then very dense cool air comes back down. These make the highs and the lows. Wind always goes from high to low. So when we start talking about weather going from either a local wind or a global wind, we're going to talk about air moving out of a high and into a low. And then moist air, less dense than dry air. So you put water in there and it actually displaces the heavier molecules, so it becomes less dense. And wind always flows from high pressure to low pressure. And there is the stop. Okay, that's the end of 12A. 2 more videos to go. Bye.